Hey guys, so let's talk about circuits. I'm going to give an abbreviated version of what we covered in class. I'm not going to get into the source and details of resistance. If you missed those notes, certainly get those from somebody else. I think it's most important to talk about series and parallel resistors. So let's remind ourselves that a battery looks like this and creates a potential difference from positive to negative. And we have a conducting wire that then goes through a resistor, which we draw as a jagged line. So a battery has a little line and a big line, and our resistor with resistance R has a jagged line. So this is potential difference V, otherwise known as EMF. And creates the potential hill for them to climb up, giving them energy. And then, of course, they cascade back down. Technically, it brings them down to low potential, and then they come back up because they go this way, if you remember. Right. Regardless, that little detail doesn't matter. What matters is that you have a power source of energy, which is the battery, and what's transforming it, which is the resistor. So the resistor transforms energy, and we'll talk about that more in class. So the most important thing is current comes out of the big guy and is represented by the letter I. That's current, and of course Ohm's law says voltage is current times resistance. Really, you should think of it as current being voltage over resistance, meaning emphasizing the inverse proportionality between resistance and current. So if you have twice the resistance, you have half the current, of course, and so forth. So let's talk about series versus parallel configurations, and we're going to talk about this implication in detail with examples in class, but let's get the notes down. So series, you put the resistors in a line. So these resistors could have any resistance values. I'm just going to have a general R1, R2, and R3. This is an R here. So we measure resistance in ohms. It could be 1 ohm, 5 ohm, 10 ohm, whatever. They could all be 2 ohm. They could all be different or all be the same. So we have these resistors and electrons are going through them. So here's the whole point. Electrons go through them with some current I. If this resistor experiences all of the electrons, this resistor will also experience all of the electrons. And this resistor will also experience all of the electrons. So the current represents the flow of electrons, and each resistor will, of course, experience all of the electrons. So in the point of view of the resistors experience the same current. So it should make sense that the series positioning orientation of the resistors results in the same current for all resistors. So I will emphasize this next point more in class, but I realized a cool way to explain it. It's if these are hooked up with some battery, the battery provides some total voltage, right? So there's some battery here that's providing some total voltage, and it'll be connected here, and we'll come back around here. These resistors transform that energy into some other form of energy. So it's like you have a water wheel transforming potential energy into some mechanical energy, or if it's a light bulb, transforms it into light energy, or if it's a toaster, it'll transform it into heat energy, or if it's a speaker, it'll transform it into sound energy. The point is that the voltage, as you remember, represents the energy, or is related to the energy, and each of these resistors takes that voltage away. So it doesn't take speed away, it doesn't slow them down. I actually said that, I misspoke in class. I think I said something that wasn't exactly helpful. But regardless, the speed of the electrons actually stays the same, and notice they have the same current. Of course, the speed of the electron stays the same. What happens is each of these resistors turns this potential energy into some other form of energy. So it doesn't turn it into kinetic energy of the electrons, it turns it into something else. So just remember that each resistor comes with a voltage drop. Right? So sorry, that was a long-winded way of basically saying there's a voltage drop for each resistor. And of course, the individual voltage of each individual resistor is the current through that resistor times the resistance of that resistor. So you can use V equals IR for the total values. So I'm creating total here, total, 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 or you can use it for individual resistors and their individual voltage drops and their individual current. Last but not least, the total voltage has to equal the sum of the voltages. Of course it does. If this goes from 0 to 10, these all have to add to 10, meaning they have to end back at 0. So a battery always, if you guys remember this in class, you're always going to have this be 0 volts over here and this be some voltage value, some positive voltage value here. Okay, that's the key point. Right. If you plug these into here, you get that the total resistance, so then you notice the current will cancel everywhere. You get that the total resistance is simply the sum of the resistances. So there you have it, nice color-coded. Current is the same for all of them. Each of them has their own individual voltage drops. So remember, series has individual voltage drops, the same current for all, and of course the total voltage equaling the sum of the voltages, and of course the resistors adding up, which makes sense because in the perspective of the electrons have to experience all three resistances. So of course this will simply act to increase the total resistance. Adding resistors in series orientation increases total resistance. Cool. Let's do parallel. So parallel is a little weirder. So parallel is where you have a separate path for each resistor. I have a really cool analogy for this to give you guys in class, but I'll wait for class to do that. I just want to give you guys the notes.
first. So we're going to do a similar analysis. And one easy way to remember this is that it's going to be the exact opposite. Exact opposite. So first, let's do the same analysis with the current. So if you're already going to notice, the current coming in now has 3 different choices. So like a river splitting into 3 separate rivers, you will get 3 separate currents through each individual resistor, 1 for each individual resistor. So here we can write it like this. The current splits such that the individual current, so we're going to come up with an analogous equation for current here, clearly solving for I. We divide by R and we get V over R. What does this say? This says that the bigger resistor has less current. So if you have a bigger resistor, it will experience less electrons. Of course it will, because those electrons don't want to go towards that resistance. Eventually, some of them will, so probability states that a certain percentage will, and as we're going to see, that percentage, that exact number, is the inverse ratio, right? So the ratio of I1 to I2 is simply the inverse ratio of the resistors themselves. So if R2 is twice R1, that means I1 will have twice the current, which should make perfect sense. Also, the total current has to equal the sum of the individual currents. You're not going to lose electrons, right? So this one should be super easy. Don't forget this one. But they have to add. So in this sense, all the voltages add to the total voltage. In series here, all the currents add to the total current. And of course, coming out here, you have all the electrons joining together in a big happy reunion, and they flow again, equaling some total value of the circuit. I think current is really easy, and I think it's easy to picture the electrons moving. And if you have a larger resistance, you have a smaller current, and these currents all add up to the total value. I think this is easy to see also how in series it's the same for all of them. What's a little trickier is the voltage drop. So the voltage drop for this is one gigantic voltage drop over all of them together. So this is going to take a second. All right. So you might ask yourself, does that mean that it's V over 3 for each? No. It's shared. V, 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 all shared at once. So does that mean it's 3V total? No. It is simply V, a certain voltage drop. So say it was, I don't know, 10 volts. That means R1, R2, and R3 would all share 10 volts of potential difference all at once. They would share it. It's like you all have the same thing simultaneously. You don't split it into 3 separate pieces and you don't count it 3 times. It's like they all have it simultaneously. It's like how we all experience time simultaneously. I like the analogy of time. I mean, the analogy of waterfalls and height is really the best way to do it. If you have 3 parallel waterfalls, right, you have one here, and then you have another one here, which has more flow, and then another one here, which has even more flow, and they all fall the same height, right? You can have 3 different resistances, 3 different currents, but they all have the same change in height, right? You can imagine that. It's like we're all experiencing time simultaneously. You and I don't divide time in half. We both experience the same amount of time pass at the same increments. So it's kind of like that. They all share one gigantic voltage drop. So the key thing, this is the most important thing for parallel, is that the voltage is the same for all resistors. And last but not least, notice how this equation with this results in V over R total. If we plug this in here, equals V over R1 plus V over R2 plus V over R3. So notice how the V's all cancel, and we get that the inverse of the total resistance is the sum of the inverses of the resistors. So this is how you combine resistances in series. Here's how you combine them in parallel. So if this was 2, 3, and 4, you would say 1 over 2 plus 1 over 3 plus 1 over 4 equals 1 over R total. Add those fractions with a common denominator, and of course solve for that. If you want to do the algebra on your own, you can show that if you solve for R total and you only have 2 of these, so if say you get rid of this one and you only have 2 of these, what you can show is that it equals product over sum. If you guys want to do that, find a common denominator, R2, R1, and this would be R1, R2, and you add it up, and then you flip it, you get this. I wouldn't write this in your notes, but you can write this in your notes. Don't do that. Erase that. There you go. Cool. If you have questions like about this math, or if you have questions about what the heck I meant by this shared voltage drop, or I hope some of this made sense. If you have questions, bring them to class. I'll be happy to answer them. This is the bulk notes that we're just going to practice again and again and again in class. So I hope this worked out for you guys, and I'll see you tomorrow. Thanks.